Hi, I'm Jahn, and today I'm going to be giving a presentation on fractional calculus. If I were doing this live, I would be able to make a PowerPoint, and if you had any questions, you could stop me, but that's not really an option given our present circumstances. So I'm going to present this paper directly, and then if you have any questions, you can pause the video and read the paper, or go back to a section I referenced earlier and read that, and that should clear up any questions. It's not ideal, but that's what we're going to have to do. Time is something of a concern, so I'm going to go through this fairly quickly. I'm just going to point out a couple of major things, do a few proofs, and call it good. Okay, so this first paragraph is talking about traditional calculus and saying why it would be nice to have a fractional calculus. This second paragraph briefly outlines how we construct a fractional calculus, but I'm going to show that to you, so don't worry about it too much. I'm not going to talk about notation because I'm going to tell you every time notation comes up, so I'm not going to present that either, with the exception of saying there are a lot of improper integrals in this presentation. Understand that I'm treating them properly. I'm just not writing that out explicitly because that would be tedious. Okay, so first thing we need to talk about is the Koshi formula for repeated integration. And that's a way to take many iterative integrals. So like if you have the fifth integral of function that you want to find, you can compress that into one integral, which is really nice. Here's the definition, and we'll prove this in a second. But before we prove it, let's do an example. Here are a couple of simple ones, but we'll get to one that's kind of interesting. Everyone who's taken Calc 2 knows that if you take four integrals of a trig function, like sine, you get what you started with. So we'll see if that actually happens. This J notation just means we're going to take the integral here, the fourth integral of f of x. So f of x is sine of x, and then we can take this, plug it in here. This is the definition of the Koshi formula for repeated integration. So to get from this step to this step, we just add stuff together, nothing too complicated there. To get to this step, what we do is expand this and realize that 3 factorial is 6. To get to this step, we push the sign through. To get to this step, we complete the integral. And to get to this step, we apply the limits. I'm going to note here real quick that this bottom A contributes arbitrarily to this constant of integration. So don't get too caught up on that. You could always add another integral and make A whatever you want. So don't worry about it too much. If you have any issues with that, feel free to email me and we can hash it out. Okay, so we apply the limits to get to this step, and then we have a lot of things, like notice these two cancel out. So after we do all the cancellations, we're left with this. And of course, these 6's cancel each other out, and we get what we expect. So that's good. Okay, the Koshi method for repeated integration is really fundamental to fractional calculus, so I'm going to actually spend the time to prove it. But before I do that, I need to prove this property, which I will do here. Okay, so starting with the left-hand side, I have this, and then this is just the definition of the derivative. So then I add and subtract this middle term. That's the same as adding 0, so that's a legal move. And then to get to this line, I do some associativity. To get to this line, notice that this is an integral from a to x plus h, and this is an integral from a to x, and it's the same thing inside of the integral. So if I take the difference of these, I get an integral from x to x plus h. And on the right-hand side, all I do is I combine these integrals. And this comes from average value stuff, which you probably learned in Calc 1 or maybe Calc 2. And this comes from just pushing this h through with linearity. There are some requirements for doing some of these things, and feel free to read through those on your own time, but I'm not going to get too deep into why some of these things might cause problems. Okay, so then now to get to this last step, we can apply the limit. So the limit as h goes to 0, well, we know our t is trapped in here, so that means t is going to go to x, and x plus h as h goes to 0 is also going to go to x. So we get this on the left-hand side, and then this integral becomes this, because recognize this, not including the integrand, this is the definition of the derivative again that we used at the beginning. And it's actually the derivative with respect to x. So this is the partial derivative of g with respect to x of x and t. Okay, so that's what we wanted. Now we can actually prove the Koshi method for repeated integration. The way we're going to have to do this is a math induction proof. So we need to start out with some Pn, and we're going to prove this for all n in z greater than or equal to 1. Okay, so starting with our base case, we'll just take this right-hand side here, plugging in 1. Okay, pretty simple. Simplifying gets us this, and this, of course, is the first integral of f of x. Good. Okay, now we can assume pk is true, and we want to show pk plus 1 is true. So just writing that out a little bit more explicitly in this line, I'm going to start with the right-hand side. This is our p of k plus 1. It's not really the right-hand side. I don't know why I said that. Sorry. This is p of k plus 1. And notice there's a d dx in front. The reason that's going to be there, the reason that is there is going to be clear in a second. So to get here, I just simplify all these k plus 1 minus 1s. And then to get here, recognize that this is just some function of g of x and t. So why not just say that and do the substitution? Okay, so now we're here. We can pull the k out, and I didn't write that explicitly, but it's kind of obvious. So then we have d dx of this. Oh, we know what that is. We just showed it. It's this. So I'll take this down here, plug it in. Of course, the k stays in front. So now we have this line. And let's think about this for a second. What is g of x and x in this case? Well, if we plug in x here, this is very clearly 0. So we get 0. And what happens if we take the partial derivative of g with respect to x? I'll let you do that on your own time, but it's very easy. It's what we get here. Okay, so now we can combine this k and this k to get this. And the right-hand side stays the same, so now we have this line. And hey, this is the kth integral of f of x. Nice, okay. And we had this d dx in front, so keeping that in mind, we know that this is true. So pk is true, implies pk plus 1 is true, and the induction is complete. This is proven. Good. Okay, let's talk about the gamma function very briefly. This is the definition of the gamma function. Kind of the point, as far as we're concerned, is that the gamma function can generalize the idea of factorials, which only applies to the natural numbers, to a continuous domain, and we're really just interested in this x being in 0 to infinity, although the domain is much larger. Here's a useful limit that we have to solve first before we can do a lot of things in this section. I'm not going to go through it, but you can take it to be true, or you can read that. Okay, this is kind of the whole point of the gamma function, like I just said, as far as we're concerned, is that it generalizes factorials to a continuous domain, and obviously it needs to match up. So here we show that it matches up. It's another math induction proof. It's a fairly straightforward one. Feel free to pause the video and look through it. It's actually easier than math induction that we already did. Okay, here's a useful property of the gamma function. We're not going to use it too much in what I'm going to present, but we do use it extensively throughout the paper. And this comes pretty much directly from this and the previous claim. Okay, here's a nice little rule that lets us take the products of gamma functions. And this is the beta function, which is defined here. It is starting to get kind of to the advanced math stage, so we're not going to talk about this. But it's nice to be able to take products of gamma functions, so we have it. Okay, so if we want to actually calculate some of these, it would be nice to actually see it in action. We're not going to do this one because it's too simple. We're not going to do this one because it's too simple. Let's do this one. It's kind of an interesting one. So let's take gamma of 6. Hopefully we know that that should be 5 factorial. We'll see if that's true. Okay, so here's just applying the definition of the gamma function and simplifying gets us this step. Then doing the integral, this is integration by parts via tabular method, and I have the table below, so in a second you'll be able to see that. And then we apply the limits. Okay, here's the limits all applied. Notice this all is limits as z go to infinity of negative z to some power e to the negative z, which we showed above is 0. So these all go away. And we have a lot of things multiplied by 0 on the right-hand side. Actually, the only thing that's not multiplied by 0 is this term. So we get 120, which is 5 factorial. Good. Here's that table I promised. Okay, here's one that we're going to use a lot through this presentation, but I'm not going to be able to show it to you because it does rely on the beta function. But it's actually fairly straightforward. So if you buy the beta function stuff from earlier, you'll buy this no problem. Here's one that we can't actually solve analytically, so I did it numerically. Most arguments for the gamma function I can't solve analytically, and this is just an example of one of those. But it is kind of nice that the value that we get does fall between these two things, which is kind of what you would hope for. Okay, now we can actually do some fractional calculus. So as shown earlier, this is the Koshi formula for repeated integration. It would be really easy to generalize this to a continuous domain if we just say generalize this with like maybe an alpha instead of a k and change this to the gamma function. And that's actually exactly what we do. So now we have the definition of the fractional integral. That was easy. Okay, here are some tools that we're going to use to calculate these. These are semi-factorials, but we won't worry about that too much for the presentation. If you want to pause it and look through it, go for it. But we'll keep to easy ones, so these tools won't be necessary. Here's the reduction formula. Again, useful, but we're not going to worry about it too much for this presentation. We'll stick to easy integrals. And here's combinations of semi-factorials and the reduction formula. Okay, so we're going to do an example of a half integral. We mostly stick to doing half integrals because analytically I can find this this gamma function of 1/2, but I can't find the gamma function for most things. Okay, so let's take two subsequent half integrals of a constant. Let's let f of x equal 5, then the half integral of f of x is given by this. This is just the definition. And to get this, what we end up doing is recognize this from above. We solved that already, and simplifying this. Then we're going to do a u substitution, of course, changing our limits of integration. And here's that after the integral, applying the limits here and simplifying gets us here. Okay, that doesn't really tell us anything. I mean, it's cool that we can do that. But let's take this down here, call it g of x, and then take another half integral. So here's applying the definition again. And let's see, this is just simplifying half powers and writing things a little bit nicer. Here we have a triangle. I haven't shown you the triangle yet. Hopefully I can fit it in here. Yep, here it is. So if you're going to follow this extensively and pause the video, I'd recommend you copy down this triangle. We use it a lot. So here we do the trig substitution. Here we simplify some stuff. Here we simplify some stuff. Here we simplify some stuff. I'm sorry there's a lot of simplification steps, but it's worth it. So this integral, once we solve it, we're going to get 1/2 of pi over 2. This is reduction formula stuff, but you can easily solve this integral and see that this is true. So I'll let you do that, and I actually have it later in this presentation, even if you don't believe me. And that gets us 5x. So let's think about what that was that we started with. We started with 5. We took two half integrals, and we got 5x. That's kind of promising. We'll just keep that in the back of our minds. Here's another half integral. There's a couple of these in here, but we don't have time to go through them all. Okay, I made a nice graph of this happening. I actually took a lot more half integrals than I have in this paper. And if we start with f of x equals 1, that's this constant, then we can look at 1/2. And notice this is kind of halfway between a constant and a linear graph. So that's interesting. And then if we look at 3/2, that's kind of halfway between linear and quadratic. And then we look at 4/2, that's a quadratic. We look at this, that's kind of halfway between a quadratic and a cubic. And this one's cubic. So everything works out really well, exactly like you'd hope it would. And I made a GIF of this changing. Feel free to look that up. Or maybe I'll try to see if I can get them to distribute this with the paper attached so you can just click the link. Okay, let's talk about power rules, or at least one power rule. Power rules in traditional calculus are really useful for finding integrals or derivatives of powers of x like we have here. This is kind of a limited power rule. We can't use it in very general cases, but we can use it in a specific case where we want to take half integrals of powers of 1/2 or whole powers. So before we get into this too far, let me just introduce some notation. Here we're going to let f sub m equal this. Okay, that's pretty easy for m in this domain. And here's something that we would have talked about in the reduction formula section, but we didn't. It's just notation. know that this means this for n in here. And it's easy. I'll take care of you. I won't do any integrals that are going to surprise you. I'll do them manually. So let's see here. This is my claim for what the power rule is going to be. Let's see if I can't make that happen. Here's the left-hand side. Here's the definition of the fractional integral. Here is just rewriting it a little bit nicer. Here is the trig substitution with that same triangle again. Feel free to go back and look at it. Here is writing things more nicely, canceling stuff out, etc. Here's the 2. Here is writing stuff out a little bit more nicely, again, combining stuff, pulling the x's in front. And note that this I defined to be equal to this, and this can be written as this. Okay, so yeah, it worked. That was fairly easy. Let's verify it using the same integral that we did earlier, just because, why not? So what we did earlier was the half integral of 5, written in this notation, that's written as that. So the half integral of that, here we apply linearity to get this step. Linearity still holds here. Here we do the power rule to get this step. Here we have this. Now what is I of 1? I wrote it over here for you. Very straightforward integral. Just integrate this. You get this. Apply the limits. You get this. Okay, it's 1. And f sub 1 can be written as this. And that's what we got earlier. Good. Okay, what happens if we do the half integral of that? We'll take this, put it in here, and we do another half integral. Well, we know this comes from here. Then we apply linearity to get that out front. Then we're taking a half integral of this. Okay, well, we have this power rule. It's kind of the whole point, so let's use it. And we get this. Okay, what is I sub 2? Well, I have that integral for you as well. It's very straightforward again. This is a power reduction formula that you would have learned in Calc 1, I hope. Do the integral, apply the limits. This is what you get. Don't worry about that. That's a reduction formula, but we'll do it this manual way. So if we take this and multiply it by these, we get 5 in front of our f2. And rewriting that in terms of x instead of this f2 notation, we get what we want. That's good. Okay, we can't use that in many situations, but it would be nice if we had a power rule that we could use in many situations. So that one was limited to alpha being half powers, alpha being the power on the j, and beta being half integers or integers, beta being this number on the x. So it would be nice if we could do something in general. Here's a power rule for alpha greater than 0 and beta greater than -1. So obviously this is a lot more general, but it does kind of get ugly and we don't really have time to go through it. So I'll leave that to you. It's fairly simple if you're comfortable working with the gamma function. And of course, we verify the integrals that we did before. Okay, here's another proof. This is showing linearity of fractional integration. So if I take the integral of an integral, it does add up just like that, kind of like we would have expected from what we've done so far. Unfortunately, this is quite long, so we're not going to have time to prove it. And it does use the beta function. So we'll skip it, but it's kind of nice. Here's the figure for changing the order of integration in the above proof. And since I'm a physicist, we have to, of course, talk about the application of this. So this was figured out by Niels Hendrik Abel, and basically this is Abel's mechanical problem is what it's called. And he wants to know if we have a particle here constrained to move along this curve under the influence of gravity, how long does it take to fall a vertical distance? So we can find that. First, we recognize that energy for the particle is conserved. So 1/2 mv squared equals gravitational potential energy, where y is some starting point and y naught is some starting point, and y is where we are now. Note that the particle is constrained to move along a curve, so v is going to be given by this, where s is, of course, the curve. So we can combine this, we can combine this and this to give us this equation. We can solve this for ds over dt, which gives us this. And we know that this is going to be true. ds over dt is going to be less than 0. So we don't have to worry about the plus or minus. And solving for dt, we get this. We don't really care about ds, so we don't want this ds on the outside. We want a dy on the outside, so we can do that with the chain rule. Fairly straightforward. Recognize that ds dy is a function of y, so let's just write it as that. And then if we want to figure out the time it takes for the particle to fall from a starting point to some final height, let's call it A. We just do the integral, add up all the dt's. We know what dt is. Let's just plug that in right here. Okay, now we have that. And let's get rid of the negative because that's annoying by flipping the limits, flipping the integral. And let's just pull some stuff out because why not? And hey, look at this. Hopefully this looks familiar. That is the definition of the half integral in there. And then there's some constant of proportionality in front. So we have an application of fractional integration. That's actually not that difficult. Okay, let's talk about fractional differentiation. So this does kind of get a little bit more ugly than fractional integration, but it's defined as the alpha. Okay, let me start over. The alphth order derivative is defined as the nth order derivative of the integral of order n minus alpha, where n is the floor of alpha plus 1. So that's it in plain English, and here it is in math speak, which is a little bit more helpful. This is valid for actually alpha including 0 to infinity, so that's nice. And of course, we're going to assume sufficient differentiability throughout this section. Okay, so let's do the same function we took the half integral of, just because why not, and let's take the half derivative. So here's the definition, here's plugging stuff into the definition, here's adding stuff together, here is applying gamma of 1/2, we actually know what that is. Here's the integral being solved. Well, we're not solving it explicitly because we've already done that. Feel free to pause it and go back and watch me do that. And here's this. Okay, well, that's not really interesting again. Well, I mean, it's kind of interesting, but it's not enlightening, we'll say that. So what happens if we take another derivative of it, another half derivative? So here's the definition. Here's plugging stuff in. Here is pushing stuff through. Here's the integral solved. And taking the derivative of a constant gets us 0. Okay, well, that is kind of what we would expect from taking one integral of 5. Excuse me. Done this too many times. Okay, so here's another one that you can feel free to look through if you'd like. And here's graphs. It looks very similar to the graphs of the integrals. However, here we start with the cubic and we work our way down instead of starting with the constant and working our way up. Okay, here's a power rule. We do both power rules again. Power rule for half derivatives of half powers or integer powers. And that's nice, works out well. We verify it. And we have a more general power rule that works for things in here. This does get quite ugly. We have to use this pi notation. There's no way around it, unfortunately. Like I said, derivatives aren't quite as fun as integrals. And verifying it. Okay, that's nice. And here's just one more derivative for bonus. It's a bonus derivative. Okay, so it is kind of nice that I can prove that if we take the fractional derivative of order m, it's equivalent to the nth traditional derivative for m in this domain. And that's fairly easy to do, but we won't take the time to do it. So at this point in integration, I talked about an application. The application of fractional differentiation is way beyond the scope of this paper, but if this is distributed along with the paper, feel free to click on that link and you'll be able to read it yourself. Okay, so did you notice before integration was good for alphas in this domain and differentiation was good for alphas in this domain? Wouldn't it be awesome if we could combine them and have, say, an arbitrary power in R, all of R, and then we don't have to worry about if we're integrating or taking the derivative? Well, we could, and we're going to call it a differintegration. And here's the definition. For gamma less than 0, this is the same as this. Awesome. For gamma greater than 0, it's the same as you would hope it is. It's the derivative. Awesome. Here is a graph that tells us how integration over here kind of comes into differentiation over here and how it smoothly transitions. We won't be able to talk about that, but it's interesting. It does transition smoothly, and it kind of gives you an idea of why differentiation is so much harder than integration. Okay, so a point of notation about different integrals is we always keep the power or the variable in the power positive, and if it's going to be an integral, meaning this whole power needs to be negative, we denote it with a negative in front. So here is the proof I said I liked earlier. It's linearity of fractional integration, and written in terms of differintegrals with the d operator, we keep alpha or beta positive and put the negatives to denote that it's actually an integral. So that's good to keep in mind. Here's a nice proof that I can take out m traditional derivatives on the left-hand side of a differintegral. That's very useful. It does kind of start breaking things up into cases once we get into differintegration, because we have to be concerned about whether we're integrating or differentiating, and we can't use properties of differintegrals when we need to use properties of integrals because those have already been developed. So we have to build up our differintegral properties before we can use them, is basically what I'm saying. Okay, I am going to tell you about this differintegration proof because it's fairly short and we can use differintegral operators, and it's kind of nice. Okay, so I'm going to claim that fractional differentiation is the left-hand inverse of fractional integration. So let's have some fractional derivative on the left hand of some fractional integral of like order. Okay, so are we ready? Well, I didn't prove it, but I flashed it for you in 6.1.1 that I can take out n traditional derivatives from a differintegral. So that's what I do here. And then that makes this an integral and this an integral, and we already have properties of integrals. This one is shown here that we can just add these up, so that's nice. These alphas cancel each other. We're left with this, and then we have n derivatives of an nth integral, and from traditional calculus, we know that gives us f(x), which is awesome. Great. Okay, here's that in a more general sense. We have a general derivative of a general integral, and this breaks into cases, so we won't go over it, but it's fairly simple if you'd like to. Once we start putting derivatives on the right-hand side, it gets ugly. We have sigmas and garbage shows up, and there's unfortunately no way to avoid that. But if you'd like to read through this on your own, you may. This does get somewhat ugly. Okay, so now we're going to take a general fractional integral of a fractional derivative. Again, somewhat ugly, but since we already built the case where we have like orders in the previous proof, it's a little bit easier because we don't have to do that again. So two cases, and here's the derivative of a derivative. This is kind of the last combination of composition of differintegrals that we could be interested in. And it's actually a fairly easy proof, but you have to understand the sigma notation, the two ones we just did, so I won't show it to you. And I'd like to thank these people for helping me with this project. Thanks.